All right, class, so I'm just going to record the notes here for you for logarithms, and this should assist you in completing the work. So let me open this up so we can start the notes, and we'll start with section 4.2. And this is logarithmic functions. All right, and so these two are related to related cousins in terms of the lesson from 4.1 and 4.2. In the lesson in 4.1, obviously we did exponential. Logarithmic functions are inverses of these. So one thing you need to know here is in this case, as I stated earlier, these are inverse functions when I compare exponential functions and logarithmic functions. So the inverse of an exponential function, and if you remember, inverse functions are 1-to-1. So the inverse of an exponential function is a logarithmic function. I'm just going to put f of x or function. Just note that that is the same thing. And this means that these are 1-to-1 functions. Now, I'm going to show you, as I do this, some notes that I want you to take away. One of them is basically how do we graph these? And let me find, I think it's example 6. So I'm actually going to do example 6 first because it ties to this part of the notes. And so in example 6, we want to graph. And in this case, they give us f of x is equal to 2 raised to the x. And they want us to graph on the same graph where you have g of x is equal to log base 2x, and they want it in the same rectangular coordinate system. Okay, so take a look here for a second, and let's do an xy grid of 2 to the x. Okay, so I'm going to create a little xy template. This is going to be for this one right here. Okay, so let's say I choose again -2, -1, 0, say 1, say 2, that should be enough. And given this information, obviously I would plug that into the equation. So 2 to the -2, 2 to the -1, 2 to the 0, 2 to the +1, and 2 to the 2. So obviously I have my numbers, which in this case would be 1/4, 1/2, 1, and then 2, and then 4. And you know what, let's go out one more, and I'll do 2 to the 3rd, which is going to give us 8. Okay, so when I graph this, I can actually go ahead without doing any math. Look at what I'm saying. So you make the severe connection here. Let's go with purple. So I'm going to graph the logarithmic function, and notice that I'm not going to even bother doing any substitution or any math because these two are inverses of each other. Because that is the case, notice that I'm literally going to say that the y terms from that function original, the y f of x is equal to 2 to the x, the y terms become the x terms. Okay, so if you notice, I'm literally matching this column to the x column, and my y values transfer over as well, and they literally are inverses of each other. One is to 2. Sorry, 0 is to 1. 1 is to 2. I think I'm having a little bit of a mix-up here. So 1/4 is to -2 as 1/2 is to -1. as 0, or in this case 1 is to 0, and then 2 is going to be linked to 1. So that is where the mistake is for me. This is 1, this is 2, and this is the 3. Okay? And when you graph it, you're going to see right here on the graph that as a graph, the original function starts with the -1, -2, then 0, and then I go to where x is 1, x is 2, x is 3, and this goes as high as 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I know that I'm as high as this point here, right? So this should match if I lightly kind of like align it. At 2, so I'm over here. So 1, 2, 3, 4. When x is 2, y is 4. So I'm here. Okay, and then we have 0, 1. And then the halves, which you're going to basically just try to estimate this. So let's assume half is here. Let's assume a quarter comes closer. And obviously these are going to dip accordingly. So this is generally the 2 to the x function, where y equals 2 to the x, or f of x, which is equal to y, equals 2 to the x. So now if I draw the reverse of this, notice that when x, and I'm going to move this over a little bit. So if I stretch this out a little bit, just this side here, let me open that up again. So I'm just going to stretch that out just a lot, enough to fit the 3, 4, 5, 6, 7, and 8. So 4, 5, 6, 7, and 8. So we know that we have up to 8 for the x's, so that's why I stretched it. And obviously this goes on infinitely, so don't worry about that. Just know that this is -3, -4, all the way to -infinity. And on this side, this continues to positive infinity, right? Okay, so we can assume in this case that when x is 8, which is way over here, y is 3. So now I'm going to stretch this all the way over here. And so that's my point where I have x is 8, y is 3. Notice that over here, this was when x was 3, we have y is 8. Actually, that goes with this one. So this is your 3, 8. Let me erase that and do that again because that looks sloppy. So this is where you have 3, 8. So these guys literally are inverses of each other. All right, the next point that I'm going to use, when x is 4, in this case we're at 2. So if I match that up, I'm about here. So remember that this is the point 2, 4, and this is the point now where you have 4, 2. So that's its inverse. The other point is when x is 2, y is 1, so I'm here. And of course, when x is 1, y is 2, so I'm up here somewhere. That's another point. Those are reverse of each other, inverse of each other. When x is 1, y is 0. When x is -1, I'm at about a half. So actually, when x is a half, I should be at -1, so I'm here. Let me erase this point. This point does not belong there. Okay, and the other one that we need is when x is a fourth, so imagine coming in just a little bit more, we're at -2. So you can see this actually will go this way. Hence, these are inverses of each other. If you wish to try another, you can try this one. Just stop the video and continue with that. And so the try question was simply graph f of x is equal to 3 raised to the x, and graph g of x, which is equal to log base 3x. And so we're going to do the same thing. We're going to graph it on the coordinate system just like I did here. Okay? So you can pause this and look at it as you need. I'm going to move on with the notes. So let me go back to the notes. So that was point number 1 of that part. So we just said that they are 1-to-1. And so notation wise, I just proved that. So then I'll hop over to number 3. So I gave you number 1 or number 2, which is the graph where we reverse x and y respectively to obtain the inverse, or to obtain the graph of the logarithmic function given that you have the exponential. So you have the exponential values. All right, so let me make some room here, and we'll start with point number 3. So point number 3 is that if I have f of a that equals b, then f inverse, which is this notation with the little -1, b is equal to a. That's what we just did, basically. So the domain of f is the range of the inverse. And I already showed you this because we already did this. And so what results in this case is that you basically are, you know what, let me just write out the domain of the inverse because I'm going to confuse you if I do notation. Okay. Now, how you know these are inverse functions is really easy because you can sort of test it, which is number 4, which says if I have f of the inverse, so if I insert the inverse function into the original function, this value will equal x. That's how you know. And if I use the inverse function and I place the function, the original function, inside the inverse function, this also should yield me x as an answer. And this is another test where I can know that these are inverse functions. Okay, and I'm going to show you how to do that. All right. All right, that will be coming up in a minute. Okay, and lastly, the graph, which we actually did the graph. So notice that they say as a condition that the graph of the inverse function is the reflection of the graph of f about the line y equals x. If you want to see what that means by that, let's go back to our drawing from our original where I started showing you this thought process. And I want you to consider this line right here where y equals x, which is a parent graph, by the way. That line is what they are referring to. So it reflects around this green line that you see here. All right. All right, so let me do example 1 with you, and let's talk about example 1. Example 1 starts off with some very basic concepts. So in example 1, we are going to talk about changing. So this is what you're doing here as a process. You're changing from logarithmic to exponential form. Okay, so that means that in this example, if we're going to write this from logarithmic form to exponential form, as example A will show, if I'm given 2 is equal to log base 5x, then what I like to do, by the way, you see how they gave you the value here? I like to move it to this side, and I'm going to explain it with an easier example. But basically, when we solve for this, okay, I want you to follow the logic. Basically, that 5 squared is equal to x. So as I answer this question, I would say 5 squared is equal to x. And they're not asking you to evaluate it, but we do know that 5 squared is 25, so x is 25. So when you read this x, since we have log base 5 of 25, the question is really, let's say they were asking you for the x as the response instead of giving you the 2. The idea is that 5 raised to what power is 25? So think of it as 5 raised to the x is 25. And we know that x is 2. We know that. But let's say we didn't. Let's pretend we didn't. You would drop the x down and then convert this to log of 25 over log 5. And you would get your answer, which is 2. And that's what they're asking you to do. They're asking you to sort of go around the loop. But to answer this question, to answer just simply from logarithmic to exponential, that's your answer. All right? I just want you to see the connection between the steps. Because if you don't see the connection, what good is that? For this one, they gave you 3 is equal to log base b of 64. This is a b, not a 6. I've been teaching this for God knows how many years, and I still sometimes forget that, and I write that incorrectly. Again, I don't like this over here. I don't know about you, but I like the right side to show the answer. So I kind of just move it over there. Just literally, just like the aliens took it and moved it to the right-hand side. So it looks like this now. So I have log base b of 64 is equal to 3. So again, if I'm writing it, this is logarithmic form, by the way, and now I'm going to change it to exponential. I'm simply going to say b to the 3rd power is equal to 64. So that means that b is equal to 4. And we know that because we know our powers, right? So this is the answer they're looking for. If you were evaluating it, b, the base, by the way, this is your base, is being raised. So that base raised to the 3rd power is 64. That base is 4, and we know that because 4 times 4 times 4 is equal to 64. Okay? If you didn't know this, okay, again, since our base is kind of like an x, so you kind of like have x to the 3rd is equal to 64. That's kind of how you're thinking of it. That's why knowing your powers is important. All right. And then C. In this case, they're giving you log of base 3 of 7 is equal to y. So again, remember the pattern. It's that base 3 raised to that y is equal to 7. Okay, so that's going to be a really weird number. It's going to have tons of decimals. So in exponential form, I'm going to write 3 to the y is equal to 7. Again, this is where we stop. That's the answer. I'm just taking you to the next level where you're evaluating it. So something like this, a question like this, I would drop the y, and I would say that y is equal to the log of 7 divided by the log of 3. Now, if I could indulge you in a question you're never going to forget, because we all do know that 2 to the third power is equal to 8, correct? And if that is the case, then that means that log base 2 of 8 is equal to 3. Okay, so now let's color match these. So this is your base, that's the in pink. Okay, this value, this 8, is this number here. And your exponent is 3. Again, do the math or do the pattern. 2 to the third power is 8. Is that true? Well, yes. 2 times 2 times 2 is equal to 8. All right, so that's example 1. It's not that difficult. So if we're going from logarithmic functions or form to exponential form, let's do the opposite. Let's go example 2. So in example 2, okay, in example 2, what we're going to do is the opposite. So we're going to change from exponential to logarithmic form. Okay, I used a little bit of a short term here. I just did exp and exp and log. So okay, so since we're going to do that for a, okay, so in a, again, we have 12 raised to the second equals x. Okay, so I'm going to bring this down just a little bit to remind you of how I did that. Okay, so if you follow the color pattern, you will see that this is exponential. And I want to go from exponential to logarithmic. So this is going to become log of base 12 of what number? In this case, this would be, like in this one, this would be the x is equal to, and this should be a 2 out here. All right, so again, if you follow the pattern, you will see that the color code will help you kind of like match that, right? So now that you have that, let's do B and see if you can catch B. In example B, you have b to the third is equal to 8, and we're going to write this in logarithmic form. So we're going to say log base b of what number? In this case, 8 is equal to 3. And I write it on the right-hand side. They may write it on the left-hand side. It's still the same concept, right? Okay, and lastly, example C. In example C, I have e to the y is equal to the 9, or 2 9. And I'm trying to write it in logarithmic form. And so what I should have is log base e 9. All right, and then eventually we're going to talk about when they cancel each other out, which that's coming up. All right, example 3. In example 3, we're simply evaluating, so this is quick. This is grab your calculator. So we're evaluating logarithms. Okay, and so their question stem is simply to evaluate and so we begin with a log base 2 of 16. So whenever you see something like this, I want you to immediately think, if I'm evaluating this, that means that I'm trying to find x. So that's something they're not going to give you. You have to think this. You think this part out. You write it out. And then you use the pattern. So 2 raised to what power is 16? So now I have 2 raised to the x is 16. And I know that x has to be 4. If I don't know that, then I drop the x down and I set that equal to the log of the number on the right-hand side, which is 16, divided by the log, in this case, of 2. And you should get 4. All right, so this is example A. I'm going to give you example B. In example B, I have log base 7 of 1 over 49. So I need you to think, okay, because this is where some students lose it. I know that if I set this up as log base 7 of 49, this is going to equal that x, right? And when I work this out, that means that 7 to what power is actually the positive 49. Again, I can use the process up here where I'm going to use, log of 49 over log 7. But if we know our multiplication tables, we know that that 7 squared is 49. So that x is actually 2. But that's a positive 49. Notice this is below the fraction bar. So technically, that should give you a huge hint that the answer to this part is 7 to what power is equal to 1 over 49, right? And so if we apply this, we would say then x is equal to the log, in parentheses, of 1 over 49 divided by the log of 7. And you should get x is equal to -2. Okay, so these can help you associate the number that it should be, just add a negative because it's over the fraction bar. Okay, logically, the next question says the logarithm of 25 of the number 5 is equal to, again, you're adding this part. This part you kind of like mentally add because you're saying then 25 to what power is 5. So 25 to the x power is equal to 5. Now remember, the square root of 25 is 5. So that's not 5 squared. So we know x is not 2. X has to be a fraction. Again, if you don't know that, you would say x is equal to the log of 5 divided by the log of 25. And be careful, you may need parentheses. And you should get 1/2, because basically what this is saying is, and I'll do this over here, the square root of 25 is equal to 5. That's what this is saying. Because 25 to the 1/2 really means the square root of 25, which is 5. Okay, example D. Remember, this is a video. You guys can pause it as you need. We have log base 2 of the 5th root of 2. That's what they're asking you. So I want you to stop and think, well, equals what? So in other words, 2 to the what is equal to 2. And again, I'm going to rewrite that as 2 to the 1/5. Just like the one above, where this is really a 1/2. This is a 2 in here. We don't write the square root. We don't write the 2. It's assumed. So, well, got news for you. You have matching bases. See how they're both 2? Once you have matching bases, this is your answer. X is equal to 1/5. Okay? So that should not be terribly difficult for you to process. And let's now take a look at some properties. This is example 4. in example 4, we have use the properties of logs. And so they ask us to evaluate. So for A, they give us log base 7 of the number 7. Again, if they give you this, you have to mentally say equals what? Which means that 7 raised to the x is 7. So 7 to the x power is 7. Obviously, if I say x is equal to log 7 over log 7, remember, we always use this number as the top number, right? Anything over itself, whether it's log or elephants or aliens, it doesn't matter. This should give you 1, because 7 to the 1 power, right? If x is 1, then 7 to the 1 power is 7. That's a property. Okay, and now in B, I've talked to you about anything raised to the 0 power is 1, so that's what this relates to. So here I have log of base 5 of the number 1 is equal to what? Well, 5 to the 0 is the only way that this is going to equal 1. This is the equivalent of 5 to the x is 1. So if I say 5 to the x power is equal to 1, and I do x equals log of 1 over log of 5, you should get 0. So that's not that terribly difficult. Okay, here comes example 5. And if you notice, I'm not doing the examples in the text because you're going to have so much to practice here. I think you'll be just fine. So this time we're using inverse properties of logs. And I'm just shortening the verbiage. It's logarithms, but I'll just call them logs for now. So this is asking me to evaluate. So for A, I have log base 4 of the number 4 to the 5th. And again, equals what? So that means 4 to the x is equal to 4 to the 5th. So if 4 to the x is equal to 4 to the 5th, given that these are both identical bases, well, common sense should kick in that x is equivalent to 5. And that's a property. So x is equal to 5. For part B, again, using the inverse property, I have 6 raised to the log base 6 of the number 9. Okay, and I want you to understand these two numbers right here, this log and this 6, kind of zap each other out, and your answer is simply 9. So whatever is sitting here is your answer for this property. And again, you're trying to reason it, calculate it, whatever your mind is trying to do, because you guys are really smart, I get it. But this is what it is. And basically they cancel each other out because you have a base raised to a power that's a fractional portion of itself, matching it identically. So they cancel out. And this works, by the way, anytime when your base is greater than 0. So that you need to note this right here. that this applies 4 cases for b greater than 1 and never equal to 1. So yeah, all right. So that's fairly easy. We did example 6 already. That was the graph, so I'm not going to worry or stress about that. I'm gonna stop this video here, and the remaining examples pretty much are examples. Let me see, I have example 7, example 8, which is modeling children's heights, and example 9. Then 10, which has to do with graphing as well and finding domains, and 11, which has to do with temperature. And then we're done. So I'm going to do that other half in a secondary video for you.